So first of all, thank the Gataminas for this great arrangement. And so it's my great pleasure to come here to present our recent work. So we are going to discuss the non-equilibrium classification of topological quantum phases. So, okay, so then, so what about the non-equilibrium classification? So classification means a kind of generic characterization of the phases. Actually, first I want to discuss the motivation of this study. Actually, in the kind of matter physics, so we are interested in about how to classify quantum phases. For example, for the traditional phases, we have the symmetry break phases. We can characterize the phases by local symmetry break orders, like the magnetization and the superfluid for the superconductors. And but for the topological quantum phases, it's quite different, since the characterization are not classified by local symmetry break orders, but classified by non-local topological environments. So the case that the environments are non-local, and they characterize the equilibrium ground states. This is the typical concept for the topological quantum phases. But actually for this characterization, for experimental detection, typically we can encounter the challenges. For example, the reason is because the topological environments are usually not directly measurable. And also the ground states could be hard to prepare for the real systems. Okay, but maybe you will challenge me that, for example, for the quantum Hall effect, actually it can be easily measured just by measuring the Hall conductance, right? That's true, but this is just among just for some few states, topological states, which can happen be measured by Hall response to measure the bulk topology. And also for the Z2 topology insulator, it can be you can measure the Z2 topology insulator by just measure the helical edge states. That's true. However, typically this Z2 topology insulator are always misunderstood by the quantum spin Hall. If you talk about the quantum spin Hall insulator, actually for the quantum spin Hall insulator, you require the spin conservation, and the classification is not Z2, is Z. However, if you want to confirm the quantum spin Hall, you need to measure the quantized spin Hall conductance. This will be very challenging. Actually, so far we have no idea how to measure the quantum spin Hall conductance in kinetic matter physics. So that's why I said that in general to measure the topological phases, it could be challenging in the real experiment. Okay, now, but for the coordinate items, we know that a very important challenge that we can study the coordinate system by Fourier control. So there are several interesting properties, like the coordinate items are naturally non-equilibrium, but it can be Fourier controllable, and it can have the relatively long coherence time. So actually, in coordinate items, it could be natural to study the non-equilibrium quantum dynamics for the coordinate items. So then, if we go to the topological phases, although the topological phases are defined for the ground states, but you can induce the dynamics for this topological phase and try to find if the dynamics can reveal some interesting topology of the system. If this can be done, so especially if you can find a connection between the dynamics of the topological system with the ground state. Maybe you can establish a classification of the topological phase by non-equilibrium dynamics. Okay, this is the third. So actually, this issue is a little bit different from the issue just introduced by Cooper. And so for the Cooper's introduction, you just have a many-body state for the ground state for the system, and then you induce the dynamics, and just you still look at the property of this many-body wave function and how the topology of the wave function evolves. But here, actually, we want to study another issue. You start with some initial state, and you induce the topology by quench dynamics, for example. But then, although even the topology of the many-body wave function could still be trivial, okay, because just if in the unitary evolution, but the dynamics of the state can exhibit some non-trivial dynamics. The dynamics could be non-trivial, okay? It could be topological. And this topology can be directly connected to the topology of the ground state. So if this is true, then you can establish a characterization of the topology phase in the equilibrium. This is the idea. But actually, there are a few interesting studies in the literature. So, including the work by Hui Zai and also the Winterberg's group experimenter, and also our collaboration with SQLUST for the studies. However, all these studies are valid for the two-binary models in the specific dimensions. But if you want to really establish a classification theory for the topology phase, you need to establish a theory which is universal for all the dimensions and multi-band systems, and for the general case. So this is what we want to do in this work, in this talk. But of course, I'm not going to establish a theory for all kind of topology phases. That's too big a goal. Okay, just here we want to establish the dynamic classification for the generic d-dimensional topology phase with integer invariance. Okay, anytime. Okay, so this is the situation. For example, we can give a few examples. For example, for the one-dimensional case, if you just think about a very minimal model for this one-dimensional model, it's just a spin 1/2 model. It's the two-band model. You have the spin of coupling, and in this case, you can if you the topology is very simple. You diagnose the two-band Hamiltonian. At each moment, you have a spin direction, and the spin momentum, the spin direction is locked to the momentum. So if you run it over the Brownian zone from -pi to pi, you can see that the spin can wind for one cycle. So this means that you can establish a mapping from the momentum space to a cycle. And if this mapping covers the cycle, this whole cycle, you have a non-zero winding number. Okay, so this is topological. You get the winding number. If the mapping does not cover the cycle, then you get the zero winding number, so it will be trivial. Okay, this is the minimum model. So for this case, the winding number is just 0 or -+1. But you can introduce the more generic model. The winding number can in general be integer. Okay, so furthermore, you can go to the two-dimensional case. The famous case is for the Chen insulator. So for this model, you can again, so you can find the spin direction as a function of the momentum space. Okay, then you can just get a mapping from the momentum space to the spherical surface. And if this mapping covers the whole spherical surface, you get a non-zero winding number. So this is the Chen number for the even dimensions. Okay, but anyway, the picture is very simple. I'm not going to talk too much details. Actually, just now, Nico has given very nice introduction to the topology, so I don't need to give much more introduction. But now we can go to the for a generic d-dimensional case. So for this generic d-dimensional case, we can write down the Hamiltonian in terms of the h dot gamma. Okay, this gamma is a generic the matrix for the gamma matrix. For the one-dimensional and two-dimensional, the gamma matrix you can choose the Pauli matrices. Okay, this is very simple. It's just introduced. But if you go to the three-dimensional and the four-dimensional, you will see that the minimal case, the gamma matrix should be the typical Dirac matrix. It should be formed by 4x4. It's the two Pauli matrices. One Pauli matrix can be the real spin, another Pauli matrix can be the pseudo spin, like the orbital or other issues. Anyway, and furthermore, you can go to the high dimension cases. I want to emphasize this is the minimum model for the different dimensions. But once you can classify the topology phase for the minimal Hamiltonians, and all the generic case can be decomposed to the Dirac sum of the minimal situations. But anyway, if you want to know more details, you can check this paper. So here we just introduce the minimal case, and if we shall establish the theory for this Hamiltonian. So even for this minimal Hamiltonian, you know the generic winding number, the topology invariance can be for the winding number for the ordered dimensions, and for the nth number for the even dimensions. But the winding number, the topology invariance is still complicated. So then the first question is, can we simplify the characterization of the bulk topology of the system? So to simplify the characterization of topology, we shall introduce a very important concept which is called the Bending inversion surfaces. So what's the Bending inversion surface? Actually, you know, just for this H vector, for the d-dimension case, it has the d+1 axes. So we decompose this H vector by two parts. One is the H0, the remaining is the HSO. So H0 can be used to characterize the band dispersion. Okay. So then this HSO characterizes the spin orbital coupling. So it means that the coupling between different bands. Okay. So now then the bending inversion surface is that for all the momentum points which have vanished H0, if H0 is 0. So for all these momentum points which is defined as the bending inversion surface. Okay, actually we can have very simple intuitive understanding for this bending inversion surface. For example, for this one-dimensional case, just for this model, if you have this H0, for this one, actually this is just characterizes the dispersion for the spin up and spin down bands. If the magnetization is very large, then the two bands will be far separated. You don't have band crossing, right? Okay, but if the magnetization is smaller, then they put together, then the two bands will be where you have the crossing between the two bands. So the crossing point actually is the band inversion point. Okay, the reason because this band inversion within the points and outside the points, the energy of the two bands are inverted. So this corresponds to the band inversion. So band inversion is a very, I guess the band inversion is familiar to you guys if you are familiar with the topology insulators. But however, here I'm not just use the band inversion, this phenomena. I use the band inversion surface, this concept. Okay. So also for the two-dimensional case, you can, if you have the band crossing, this band inversion surface is just the 1D ring, like this kind of structure. Okay. Now, once we have this concept, we can go to the main results for this classification theory. So the first result is that for the theory 1, that you can see that for the d-dimensional topology invariant, the 1D number or 10 number, it can be generically reduced to the d-dimensional invariant defined on the band inverse surface. That means that actually for the d-dimensional system, the topology invariant is defined on the d-dimensional the space. But actually, this d-dimensional invariant can be fully reduced to the d-1 dimensional invariant on the band inverse surface. So that means that actually the topology of the bulk can be exactly corresponding to the topology on the band inverse surface. Okay, this gives the bulk surface duality. So actually, you can, this means that on the band inverse surface, you can have a non-zero winding for the spin of the field, and this non-zero winding of the spin of the field exactly characterizes the bulk topology of the original bulk. Okay, so now then furthermore, okay, so far actually all the results are quite mathematical, since you need to define the band inverse surface by specify some axis of this H vector. And furthermore, you say, oh, you have the topology on the band inverse surface. But then actually we need to answer two questions. So first of all, how to identify such a band inverse surface in a real experiment? Okay. Secondly, if you can identify this band inverse surface, how to read out the information of the topology from the band inverse surface? So actually, we must answer the two questions. To answer the two questions, we need to go to the real experiment. Now, this can be done by the quantity dynamics. The idea is that if we should start from a trivial phase. Namely, if you, for this H0 vector, you consider a large Z-mass splitting. If you have a large Z-mass splitting, then the order states will be fully spin polarized. So it must be trivial, right? So then you suddenly quench the magnetization parameter and go to the topology phase, topology region. So then you will say that you shall obtain this quantity dynamics. Now you can see that the band inverse surface and the topology on the band inverse surface can be automatically read out based on the quantity dynamics. So this is the key thing. Okay, now the first of all, okay. Anyway, you can just compute the spin dynamics of the system to do the quench. Then you can see that you will see that the spin will proceed. Oh, sorry. The spin will proceed due to this post-quench Hamiltonian. And the key thing that you will see that the spin dynamics will be very different on the band inverse surface compared with the spin dynamics outside the band inverse surface. Only on the band inverse surface, you will see that the spin polarization will be fully perpendicular to this H vector. So in this case, you will see that you can expect that the average spin polarization will be 0 over the time. But for outside this band inverse surface, you will see that the spin polarization will be non-zero over the time. So this will be different. So then we can go to the second theory for this result. So the band inverse surface actually can be characterized by the vanishing average spin polarization over the time. Okay. So in this case, so that means that after you do the quench, you just measure the spin dynamics and to measure the average spin polarization over the time. You will see that if the average of the spin polarization is 0, so these points must be in the band inverse surface. Okay, but then if the average is 0, then you cannot describe the topology since 0 is trivial. Okay, you cannot use 0 to characterize the topology. So then how to characterize the topology of the system? So then you can know that only on the band inverse surface only on the band inverse surface, the time average is 0. Then outside the band inverse surface is non-zero. That means that inside the band inverse surface and outside the band inverse surface, it will be non-zero. Therefore, we can look at another value to look at how the spin polarization changes from inside to outside. Okay, so then you just define another vector field, which is the derivative of the time average of the spin polarization with respect to the direction perpendicular to this bending universal surface. Just means this vector field characterizes the variation of the spin polarization from inside to outside, how the spin polarization changes. Okay, so this vector field exactly describes the winding on the bending universal surface. And so this vector field exactly characterizes the topology of the bulk. So, okay, so this is actually the main story of this theory. So firstly, you can reduce the topology from bulk to bending universal surface. Secondly, you can describe the bending universal surface by the vanishing spin polarization on the spin dynamics. So finally, you can describe the topology by the variation of the spin polarization across the bending universal surface. Okay, so this is the story of the whole story of this theory. So now we can give some numeric simulations for this result. Actually, we just consider this two-dimensional chain insulator for this model. You can choose the HZ as the H0. You can quench this quench HZ. So you just start with a MZ, a trivial phase to go to the topology phase, and then you can look at the spin dynamics. You can see that the spin dynamics will exhibit the ring structure in the Brownian zone. So this ring structure exactly reflects the bending universal surface, the bending universal ring of the system. And furthermore, you can look at the variation of the spin polarization on this bending universal ring, and you can see that exactly this gives a 1D winding on the bending universal ring. This 1D winding exactly describes the chain number of the original box of the two-dimensional chain number. Okay, so actually for this quench you can have you can choose any axis to do the quench. It does not matter. It does not mean that you should always choose HZ to quench. You can choose HY to quench. You can choose HY as the H0, and then you start with a trivial phase to the topology phase, and then you can see that now you can find that the bending inversion is low ring is the bending inversion lines, two bending inversion lines. Again, on the bending inversion lines, you can check the variation of this spin polarization, and on the two bending inversion lines, the total winding will be non-zero, and the total winding gives the chain number of the original two-dimensional bulk. The result is the same, but the quench process is very different. But you can use different quench process to do the experiment. Depends on which experiment can be easily done in the. Depends on the system. Okay. So actually, so we have done this. We collaborate with the USDC group to do this experiment. Just for this model, for this 2D chain number, chain insulator. Actually, we started with a deep trivial phase and go to the change to the topology phase. And in the experiment, we measure this ring structure and use the ring structure to determine the topology, determine the chain number +1 -1, and the phase diagram of the system. One thing I want to emphasize that for this measured phase diagram is highly consistent with the theoretical prediction. You can see this is the experimental result, and this is the solid curve is theoretical result. They are highly consistent, which means that we can actually use the dynamic classification to measure the phase with a high precision. Actually, for the high precision, namely, if you compare with our previous measurement by the equilibrium measurement of the phase diagram, you can see that this is the experimental measurement, but this is the theoretical prediction is completely different. Okay, so for the equilibrium measurement is completely different. It's completely not precise, but for the dynamic measurement, it's very precise. Okay, this is very different. Actually, there are some very simple reasons, because for the dynamic measurement, it can be very precise, but here it's not precise. But to save time, I'm not going to discuss the details. Okay, sorry, I knew I should neglect this one. This is another idea for the classification. Okay, so now let me go to the summary. So actually, we prove a box surface duality, which means that the d-dimensional topology phase can be reduced to the d-dimensional one. Bending inversion surface. Okay. So furthermore, we can establish the dynamic box surface correspondence. So the bending inversion surface can be characterized by the vanishing average spin polarizations in the quench dynamics. And furthermore, the bulk topology can be characterized by the dynamic topology environment defined on the bending inversion surface. So this kind of dynamic classification can give rise to the experimental schemes, which resulted in the high precision measurement of the topology phase diagram. So this gives you the advantages to precisely determine the topology of the Hamiltonians. Okay, so this is the theory, and this another theory will come out tomorrow. Okay, on the archive, and also the experimental results by this USDC group, and also the collaboration with Gilbert Zhou's group at the HKUST. Okay, to appear soon. Okay, so actually there are a lot of interesting generalizations for this theory. Since this theory is very basic, you can go a lot of interesting issues to all free Fermion topology phases and to the correlated topology phases and also the Foucault non-Hermitian and so on. Anyway, so finally let me thank my collaborators, my group in Peking University. So and for this guy, Senor and Lin Zhang and Dr. Zhang Nong, they are many involved in the theory. So also thank to the experimental groups, the Jianwei Pan's group and Shuai Cheng and Eugene Deng from USTC and also Gilbert Zhou from HKUST. Okay. Okay, thank you.